Alright friends, welcome back. In this video, I'd like to go ahead and take a second look at section 1.8 of your textbook, and in this video, we're going to specifically solve rational inequalities. So let's get started with that. Okay, so just as a reminder that we did talk about rational equations before. That was in our lesson 1.6 day 1 video. So if you want to go back and watch that one, we're going to need a lot of the skills we learned in that video to follow us here to this video. So you may want to go back and watch that. That's still same in the playlist there. So let's just kind of go through some of the steps here and just kind of remind ourselves how we did that back in 1.6 day 1, right? So the very first thing that we need to point out here is that we are never going to cross multiply to solve our rational inequalities, okay? You're going to be very tempted to, because it's going to look like a single fraction equals a single fraction, but that's not what we're going to do to solve our polynomial or our rational inequalities here. So instead, what we're going to do is we're going to get everything on one side and get 0 on the other side, okay? And so that's been the first step of a lot of the different types of examples that we've done throughout the course of chapter 1 here. So we're going to collect everything to one side and get 0 on the other. And then step 2, it says to combine everything into a single fraction. And then step 3, it says to factor the numerator and the denominator here. So let's go ahead and demonstrate that with this example here. Let's go ahead and take a look at this one, number 15. Okay? And so we're going to go ahead and perform those first couple of steps there. I'm going to go ahead and start this off by subtracting the right-hand side from both sides of this inequality here. And so when I do that, I'm just going to go ahead and have here the 5 over x minus 6 on the left that was already there. I'm going to find a common denominator here in a little bit, so I'm going to leave a little bit of space and say minus the right-hand side, which was 3 over x plus 2. And then that is going to be greater than what's on the right-hand side, but if we were to subtract that away, that would just be 0. So all we did there is we subtracted the 3 over x plus 2 from both sides of that rational inequality. Okay, so let's go ahead and demonstrate that here. All right, and so we end up with this. And what we now need to do is go ahead and continue on with step 2 of what it says from up above, which is to go ahead and get a common denominator going here. And so the way that we did this back in the 1.6 day 1 video is we just went ahead and introduced to both denominators what they were missing. Okay, so the other denominator has a copy of x plus 2, so we're going to introduce that to the top and bottom. And then over here on this other fraction, it is missing its copy of x minus 6, so we're going to introduce that to that fraction there. And then that's going to make it so that both of these denominators are going to perfectly match. It's a common denominator now, and so we're just going to go ahead and write a single denominator with those two copies, x minus 6, x plus 2, okay? And then keep in mind, the description that we want to fit in this example is we want to go ahead and be greater than 0. So we're going to keep track of that just like we did in the previous video when we were doing polynomial inequalities. Okay. Now, in the numerator here, the way that this is going to shake out is that, of course, we've got this value of 5 and this value of negative 3 since we're subtracting it away, right? So what that's going to mean we need to do is distribute that into both terms of what we have, and we're going to have the following. So 5x plus 10 minus 3x plus 18. Okay, and so we can combine some like terms there. So 5x minus 3x is going to make 2x, of course. And then 10 plus 18, that's going to make plus 28. And that is all over x minus 6 times x plus 2. Okay, so there we go. And that is going to be greater than 0. And again, we do want to keep track of that throughout the problem. So there we go. Okay, so now that we have everything condensed into a single fraction on the left-hand side, we have just performed steps 1 and 2 from the steps from up above. We're now going to go ahead and proceed on with step 3 that says we now need to look at everything in its factored form. So if you notice, the denominator of what we have is already in its factored form. It already looks like x minus 6 times x plus 2, but we just need to work with that numerator a little bit. And if you look at it closely, it's something that we could take a 2 out of both of those terms here. So I'm just going to go ahead and rewrite the 2x plus 28. I'm going to rewrite that so that I factor out a 2, and that leaves behind x plus 14. Okay, and so that is me performing step number 3, where I write everything in its factored form. And now what we'll do is we'll go ahead and proceed with step number 4, which is up here. It's going to say to set all of your factors equal to 0. Of course, these are called your critical points or your critical numbers. Okay, so all the factors that we just ended up with here, let's make a nice list for ourselves of all of the numbers that are critical in this problem. Okay, so those, of course, would be just all of the numbers that make each of our factors equal to 0. So if we take a look at the x plus 14. The number that's going to make that 0, of course, is going to be negative 14. And so that's going to be one of our critical numbers. X is equal to negative 14. Another factor that we have is this x minus 6. The number that's going to make that equal 0 is going to be x is equal to positive 6. And then, of course, the remaining factor that we have there, the x plus 2, that's going to be a negative 2 is what would make that equal 0, okay? So these are each one of our critical numbers. Now, this is going to be a part of the problem-solving process that is different from the last video when we talked about polynomial inequalities. Okay, if you were to actually go ahead and plug in each of these numbers into this rational expression, which in terms of plugging in, we'll just go ahead and go with this one that we finally ended up with here. If we were to plug these back in, of course, negative 14 would make the numerator 0, and therefore it would make the whole rational expression equal 0, okay? And if you take a look at the description that we're trying to fit in this problem, you can see that that's not really what we want. In this problem, we wanted to specifically be greater than 0, okay? And so that is not going to be one that we are going to shade on our number line when we get to it later. Which, matter of fact, let's just go ahead and draw that number line here really quickly, right? So we're going to go ahead and mark all of our critical numbers. So we have negative 14, we have negative 2, and then we have positive 6, okay? What we just learned is because when we plug in negative 14, it's going to make the whole thing equal 0, not be greater than 0. We're going to have an open dot at that value, okay? If we go ahead and take a look at the other critical numbers that we've got here, these would be numbers that make things in the bottom equal 0, which would make the whole bottom turn into 0. And remember that we can never have a denominator that's equal to 0. So what that's going to mean is that these two values here are going to make the rational expression undefined. And of course, if we are undefined, then we are not greater than 0, so that's going to mean that these are some numbers that on the number line we are not going to be filling in. We're going to leave some open dots on these numbers here as well, okay? And so let's go ahead and signify that over here. So we have an open dot at negative 2 and an open dot at positive 6, okay? So that leaves the entire rest of the number line for us to test, okay? So we're going to pick a candidate that lives in each one of these regions on the number line. So to the left of negative 14, in the middle of negative 14 and negative 2, in the middle of negative 2 and positive 6, and to the right of positive 6 there. Okay, so just make your life easy and pick some candidates that are really close to these boundary numbers here. So I might just go ahead and pick these examples really quickly. And we are going to plug each of those into this yellow version of my, my rational expression. And we're going to see if we get a conclusion that ends up fitting the description that we want. We're going to see if this ends up giving us something that's greater than 0. Well, I already did that in the calculator to just kind of help us save some time in the video here. So if we take a look at these results in the calculator real quick, we can see that I'm testing each one of my test values there in yellow. I'm plugging them into the rational expression, and I'm getting these results, okay? And so we can see here that we have some of these results being numbers that fit our description of trying to be greater than 0, but other ones don't. So for example, we're going to have to throw out this one because that was less than 0. Same thing with this one. That's less than 0. But we are going to keep this one because it is greater than 0, and we are going to keep that one because that's greater than 0. So that's going to mean that these are going to be the regions that I'm going to shade on my number line is the regions that contain negative 3 and positive 7. So if I come back to my number line here, I'm going to go ahead and shade in those regions, because these would be regions that are a part of my solution set, okay? So, of course, that is going to be the region from negative 14 to negative 2 with parentheses around them because, remember, we're not including them. And we're going to unite that with the set from positive 6 all the way out to positive infinity. And that represents our solution set for this problem, okay? So the interpretation, again, is if you wanted to go back all the way to the original version of this inequality, if you were to plug in a number for x and get a true statement, that number has to come out of one of these two united intervals here, okay? So that would be a complete problem. So it's a little bit more work than we saw in the last video because we have to kind of get a common denominator with a couple of rational expressions, but you could see that for the most part, after that process, the problem-solving process is largely the same. So let's go ahead and take a look at that yet again here. So we're going to do another example here in the video. And let's go ahead and subtract that right-hand side over to the left-hand side, in which case we're going to end up having here x divided by x minus 2, leave a little bit of space, minus 1 over x plus 3, leave a little bit of space, and that is going to be something that's going to be greater than or equal to the 0 that we leave over with on the right-hand side. Okay, so that's the same first step as what we did in the previous example. We just subtracted the right-hand side away from both. And then we get a common denominator here, so we're going to go ahead and say we're going to multiply times x plus 3 on this first one, and then we're going to multiply times x minus 2 on that second one, just to get those denominators to match up. And if we do, then that's going to be a common denominator here for us, which we can just go ahead and write as one single fraction with a common denominator of x minus 2 times x plus 3. That's going to be greater than or equal to 0. And then remember that we're going to go ahead and distribute the terms that are in the top here. So x is going to get distributed, and since we're subtracting away the 1, we're going to interpret that as a negative 1 that's going to get distributed to both here. So let's go ahead and perform that. So that's going to be x times x, which is x squared, x times 3, which is going to be 3x, negative 1 times x, which is negative 1x, or just negative x, and then negative 1 times negative 2, which is going to give us a positive 2. Okay, and then it looks like we have some common terms that we can combine in the middle. That's 3x minus x. I'm just going to go ahead and trade that out here for plus 2x. Okay. Now, we've just performed steps numbers 1 and 2 from up above. We're going to move on to step 3 now, where it's going to say to factor everything. Well, it looks like the denominator is already factored for us into x minus 2 times x plus 3, and so we would just need to check to make sure to see if that numerator is going to factor for us. And I will give away the punchline here. It turns out that this numerator does not factor. And so when we move on to getting our critical numbers here, we're going to set each one of our factors equal to 0 and solve. And so I think it's pretty straightforward to see why x is equal to 2 would be a critical number, and x is equal to negative 3 would be a critical number, because those are values that would make the two factors that I have in the bottom equal to 0. But if I set that numerator equal to 0 and solve, so that is the x squared plus 2x plus 2. If I were to go ahead and try to set that equal to 0 and solve, that's something that I would need to use the quadratic formula to solve for, okay? So just make a note of that, QF, quadratic formula. If you were to apply that process, what it would give you is x is actually equal to a complex number, so negative 1 plus or minus I. Okay? So while we would consider those to be critical values here, unfortunately, whenever we go to the number line, our number line is only going to deal with real numbers and not complex numbers. So whenever we draw our number line here, we're just going to account for the negative 3 and the positive 2 and disregarding the complex numbers that we got here for some critical numbers, okay? And so we're going to move on to the next step of that process, where we kind of signify here that, these critical numbers that we got, these would be values that if we were to plug them in, it would make our entire expression undefined. And so we're going to have some open dots at these values on our number line here, because we can't include them because they make it undefined. And now we just need to go through and do those test regions, okay? So we're going to pick a candidate that lives in each one of these regions here, and we're going to see which one of them matches the description that we want to be in this problem, which, of course, if you look up here, that is going to be greater than or equal to 0. We're trying to figure out what outputs give us what inputs give us outputs that are greater than or equal to 0. So again, just make your life easy and test some numbers in here that are easy to test. So how about a negative 4 and 0 and 3? Pretty easy, pretty straightforward. And I've already done the heavy lifting here for us in the calculator. So we can see here that when you plug in negative 4, you are going to get something that is going to be greater than 0, which is going to be one of the things that we wanted, right? So we want to be greater than or equal to 0, and this, of course, is greater than 0, so we keep that that critical number, okay, and shade its region. We can see here that the critical number 0 is going to give us something that is less than 0. We don't want that, so we're going to disregard that, but we definitely see here that when we test 3, that is going to be greater than or equal to 0 as well, so we're going to shade the region that that came from as well here. So the regions that negative 4 lives in and that positive 3 live in, we're going to go ahead and shade those regions and then write those regions down as a interval notation, right? So negative infinity all the way until we reach negative 3. Let's see around negative 3 because we're not including it. We're going to unite that with the open interval from 2 all the way to positive infinity, again with a parenthesis around 2 because we're not including it because it makes the rational expression undefined, okay? So there would be another complete problem there, right? So again, going through those steps, you're going to collect everything to one side, get a common denominator, and then try to factor everything, set it all equal to 0 to get your your critical numbers. Put those on your number line, test your regions, and then you're going to be good to go. Okay, so 2 examples where we did that. Just to kind of flash these examples up here on the screen here, here's number 13, where it looks like for the most part, a lot of those steps have already been done for you in terms of getting everything to one side and getting a common denominator. So there would be a very quick process there. So if you wanted to pause the screen and read through that, you can. And then we'll also do that same thing for number 14 here, where we're going to flash that up here on the screen, right? So This is an example where you're going to bring 3 over from the right-hand side and then still get a common denominator and do the exact same things that we discussed, and then get that final answer of that interval from 8 to infinity. Okay? The last thing that I want to discuss here in this video is a problem like number 17 where it says find the domain of this expression. And so we've done this sort of thing before where we had some square root expressions that we were trying to find the domain for. And what we said is that if we want to avoid complex numbers, which we do, we want to go ahead and say that this part under the square root is not negative. So in other words, this part under the square root, the 144 minus 9x squared, we have to say that it's not negative, or in other words, that it's positive, greater than 0, or that it's equal to 0 itself. And that's why we included an example like this in this video, is because what we just set up for ourselves is one of those polynomial inequalities from the previous video. That's 1.8 day 1, okay? And so what we're going to do is continue to solve this using the usual steps. So we're just going to factor this expression. This actually turns out to be the difference of two squares, so this is going to factor into 12 plus 3x times 12 minus 3x. And that's greater than or equal to 0. And if we go ahead and get our critical numbers from this, then we are going to see here that x is going to be equal to negative 4 and x is going to be equal to positive 4, okay? So those are going to be our critical numbers here. And if we go ahead and draw our number line, we're going to see here that with those critical numbers, negative 4 and positive 4, these are going to be values where we are equal to 0, and keep in mind that that's okay. We want that to be a part of our description because we're trying to get greater than or equal to 0 in this context. So let's go ahead and put some solid dots on those critical numbers because that is where we, of course, are equal to 0. Okay, so we're equal to 0 here, we're equal to 0 there. And then we just want to go ahead and pick a candidate from each one of these regions and test it. So again, make your life simple. How about negative 5, and then 0, and then positive 5, which you know me, I already have this ready to go here. So if we go ahead and test those values here, it looks like I'm going to get some values that are going to be less than 0 in the case of negative 5. So we want to be greater than 0, so we're not going to do that one. We than 0 here with the 144, so we are going to shade that region where 0 belongs, but we are going to pick this region where 5 lives because that created something that does not fit our description. It's less than 0. So we're just going to go ahead and shade that middle region for ourselves because 0 worked, but these others did not. And then we're going to get our final answer there of that closed interval from negative 4 to positive 4. Okay, so it's going to be the domain of this expression. Going to be the input you could plug in for x that's going to make that yellow expression under the square root something that is not negative. Okay, so I hope that this video has been of some help to you. Again, feel free to go back and pause the screen through some of those examples and see if you can't make sense of those. And again, I'm always available to answer whatever questions you have. So thank you very much for your attention in this video, and I will speak to you guys in the next one.